Hello, this is Philip, and I want to talk about essentially the contents of chapter 27, which is how do currents actually get created in wires, and what is a good model for wires on the inside, how do the electrons flow through them, and so on. And in the process, we're going to make sense of some of the concepts that we've already used in our circuit analysis, such as Ohm's law. So, some of the content of chapter 27 we've already covered. For example, the Kirchhoff rules, right? They appear in the textbook in chapter 27. We introduced them as part of chapter 28, which we did first. So a lot of the stuff you'll find in that chapter actually you already know. The main topic that you haven't met yet is looking at more realistic wires, right? In the past, all our wires were ideal. In the past, we had ideal wires, and the thing about ideal wires, there was no electric field inside, and no potential difference from one part of the wire to the next. Of course, realistic wires aren't quite like that. In many cases, we can approximate wires as ideal because the resistance in the wire itself is tiny compared to the resistance of the thing you're going to connect the wire up to, such as a light bulb, for example. Right? So ideal wires often a useful approximation. But not strictly true. And the type of analysis we're going to do in this chapter, in this video, is actually the type of analysis that allows you to understand, for example, why a light bulb itself is nothing but a very, very thin wire. Right, so how does thinking about currents through wires actually help us understand, for example, how light bulbs work? Like, why do they actually glow? Just because a little bit of current runs through a very thin wire, the filament in the light bulb. Not strictly true. Okay, so let me get started by drawing a model for a wire. So here's the inside of a wire, one way you might visualize it. It's essentially made of atoms, right, and they're bounded to each other, right, in some way. That depends on the details of what the material is made of, but they're in some kind of solid structure. I drew it here as a sort of diamond shape, but of course realistically it's in 3D and more complicated, but it's not the point. The point is you've got atoms that are sort of equally spaced in some kind of pattern in the wire. That's what makes up the solid object. Here I drew little plus signs because they're positively charged nuclei. Of course, often they've got little electron clouds around them, if you like, right? It's kind of a model for the atom. But also they have free electrons that are just allowed to sort of zoom through the wire. What will those electrons do? Let's imagine there's a little electron that starts here. Now, the electron's going to go at a very high speed just through the wire. It's a very light particle, right? So tiny forces give it a huge acceleration, so it's going to go pretty fast. Let's imagine it starts out maybe by going this direction here. This direction. So I'm marking this with a ruler because it wouldn't be quite accurate anyway. So what's it going to do? It's going to sort of zoom through here, and it's getting really close to one of those nuclei. So it's going to get deflected. Maybe it gets deflected this way. Right, it gets super close. Then, it gets close to another one. Maybe it does this. Right? Then maybe this one goes super close, so it comes around like this. Maybe it goes this way now. Then, who knows, maybe here it does something like this. Right? Then it goes back here. Maybe up to here. And it goes around this way. And this way. So it sort of bounces around randomly. You can really think of the electron colliding with each atomic nucleus that it sort of gets too close to, and it'll randomly change direction depending essentially just on the exact angle it had when it came in, right? So this is a little bit like imagine you've got a sort of meteorite that comes close to your home planet. So here's a planet, right? Here's a meteorite. It's not gonna hit it, but maybe it goes really close and then gets deflected because of the gravitational pull. It's a little bit like that. We can say there was a collision. It's not literally bumping into it, but because of the deflection, we can treat this interaction, in this case through gravity, the case up here, so like electrostatic attraction, we can treat that as an elastic collision, right? So the electron collides elastically with atomic nuclei. It's more like a sort of flyby, but at the level of, atomic physics, it's all a bit fuzzy anyway, what exactly a collision is. Okay, so you get this kind of picture. Another electron that maybe starts out here, just for good measure, right? Might be going sort of here. That deflects it to go this way. That makes it go this way. Oops, it comes super close here. Now it's going that way. That gently deflects it and so on. So they're going to sort of whiz around backwards, forwards, and they're going to spend the same amount of time going this way and going the other way. Right? They're just whizzing around freely. Occasionally they might also repel each other. But let's not worry about that. The details here aren't very important. The main idea that we need is actually what do electrons do in the wire. The chance of colliding with a particular particle, like a particular atom, depends, for example, on the size of the atom. It also depends on the temperature of the wire, because if the wire is hot, that actually means that those particles can wiggle back and forth more, so they kind of present a bigger target area. Right? It's almost a sort of patrolling back and forth super fast because of the oscillation they undergo due to their thermal energy. Okay, so now what happens when we have an electric field in the wire? So let's draw the wire again, and this time let's add an electric field to it. So here's the picture of the same wire, and now I've added a constant electric field, and for no particular reason I decided that it should point to the left. So if this were just some kind of chunk of metal and you put an electric field into it, what is it going to do? It's going to push all the electrons that are living in here freely. I'm going to talk in a second about how that actually works, but it's going to push them this way, right? The negatively charged particles, so they go to the right. So they're going to gather here at the end of the metal, and they're going to create their own electric field because there are a bunch of electrons stacked up over here that's pointing the other way, neutralizing the electric field that was there before. So you end up with zero field inside the conductor, like you know. But suppose instead, by some mechanism, we are going to not give those electrons some place where they gather, but we're going to maintain a constant potential difference between the two ends of the wire. Now, because the field points this way, we're going to have a high voltage here, or high potential here, and a lower potential here. Of course, what is the potential? That doesn't actually matter. The important part is that there's a potential difference, of course. Okay, so let's have our little electron. Let's have it start here, right? It's still sitting in the wire, just like before. And let's say it's starting off going in maybe this direction here. Now the thing to note, of course, is that there is now going to be a constant force on the electron that's to the right. The electron experiences a constant force to the right. Because the field is to the left and the electron is negatively charged. So the electron is still going to collide with the individual atoms, and that's still essentially a pseudo-random process, right? Technically, it just depends on the impact, the exact impact parameter. That is to say, if I go back to my previous picture here, right, with this idea I had here, like the meteorite coming close to the planet, and the angle by which it is deflected depends on how close it got. For example, if say this one comes in here, it travels like this, it might end up going this way. if it came in at a sort of way closer, it would get deflected more. You can't see this, right? Or if it were to come in sort of super close, this is when you're a planet, super close, it might actually sort of end up doing this. So it depends exactly how, like, what is the angle? Is it coming straight at it? Okay, then it's going to hit. But if it's missing, the angle by which it gets deflected depends on how close it gets. And that sort of calculation you'd actually do in, say, an mechanics course for physics majors, for example. So if you are a physics major, then you might do that kind of calculation in your third year mechanics course. So it's not actually random, but for all practical purposes, it is random. Because we can't really control how close you get to the atomic nucleus. So those collisions are still going to happen, and when the electron is close to an atomic nucleus, the force between the nucleus and the electron is going to be way greater than any force due to this applied electric field. We can, by the way, write down what the force is. The force is going to be, of course, the strength of the field times the charge of the electron, which is E. Yes, I know the charge of the electron is technically minus E, but I've already said that the force is to the right, so I've taken care of that. So let's see what path this electron is going to follow now. Let's say it starts here, and once more it bumps into this one, and by bump into, I mean this gets very close enough that the attraction between the electron and the nucleus sort of dominates the motion of the electron, at least for a brief moment of time. So it might do something like this. Now it might be traveling this way. Okay, now it's traveling far away from any nucleus. So now the force to the right starts to matter. Unlike before, it's not going to travel in a straight line until it hits another nucleus. Instead, it's going to follow a sort of curved path like this. It actually doesn't curve very much if you actually look at the numbers of how fast is it going, so on. But I'm just going to exaggerate a little bit. Might curve like this. Okay, and now it's close again to an atomic nucleus. So now it does a random collision, and maybe it's now suddenly going this way. Right? Now it's going this way. Now again, there was a collision. It's now going a different direction. Elastic collision between a very light object and a comparatively heavy object. So that means, if you remember, you did a kind of calculation in 161. That means that the speed of the electron is pretty much unchanged from before the impact and after the impact. But now it's going to go in this direction, and again the force is to the right, so it's going to curve sort of this way. And it's going to, now instead of traveling, this way, it's actually going to speed up in the process, right? Oh, now it's getting super close to this one. Big collision here, so it's going to go this way, right? So it's going back. Yes, the field is this way, the force is this way, but just because of the randomness of the collision, it sometimes might end up going to the left, right? But if it were going straight left, it would be slowing down. If it's going straight right, it's speeding up. If it's going, sort of downwards, it's going to curve like this. If it's going upwards, it's going to curve like this. It's going to curve. Ah, maybe it's getting close to this one now. Okay, now it's going this way here, say. It's going to again curve a little bit to get straighter and straighter. Oh no, it's turning super fast this way. I guess it's going to go this way here. Sometimes the distance is very short, so there isn't much space for it, or much time for it to actually change its path much from the straight line. So now it's going this way. So now it's going maybe this way already, and then now it's just speeding up. Oh, there's another collision. Maybe it's going this way now. Again, now we're here. Now we're curving. And of course, it never hits the edge because there is no edge to the wire, right? It's just my 2D drawing. You can imagine it keeps going round, and so on. So the upshot is the electron spends slightly more time going right than going left. And, on average, does so with a slightly higher speed. Because it's speeding up when it's already going to the right, but slowing down when it's going to the left. Of course, that is reset every time it hits something, then essentially the direction becomes random, but between hitting one thing and the next thing, its path again changes to favor going to the right. Let me draw this on a graph. So here I'm going to draw a graph. Actually, I'm going to draw two graphs. I'm going to put the, let's call it the x velocity, and by x I just mean, this direction here, to the right, the x velocity against time. And first, I'm going to plot it without an electric field. So there's no E field in the wire. That was the first scenario that we had. So that might look something like this. It might start out, depending when I start looking, of course, it starts out here, it goes forward, a constant, the constant straight line, the constant x component of the velocity. I don't care about the y component, the up-down motion right now. I just care about how it's going to make its way along the wire. Then it collides, so maybe now it's still going forward, but not as much. So I'm actually looking at the picture here that I drew before, right? It was the picture for the wire without electric field. It's going to have big x component. Now it's going more of an angle, so a smaller x component, a bigger one, a negative. So each time it collides, right, it's changing randomly what the x component is. And the time from one collision to the next varies. Maybe it could be like this, and it's going forward for a little bit, it's going backwards again. It's going to look something like this. Sometimes it's going forward when the velocity is positive, sometimes it's going backwards. And on average, we're going to spend with this distance covered going forward being equal to the distance covered going backwards. Right, remember, velocity time graph, distance or displacement is given by the area under the curve, or the area between the graph and the axis. So if as much area above as below, on average, the electron's not going to prefer going this way to this way. Of course, there's zillions and zillions of electrons. Some of them are just by chance going to make it actually fairly far along the wire, but some others, and I mean the wire without a field, some of them are going to go the other way a fair amount of distance. Some of them, they're just all over the place. There's no overall pattern to the motion. So now let's draw the same graph, but let's draw it for the case where there is an electric field. So here's my x component. Now we have the situation with the electric field. Right? So let me plot my axis. So now what we have is a constant acceleration to the right, in the positive direction. So now, if I'm going to try this, I'm not going to stick with the exact pattern, but you can do it, but you get a rough idea anyway. It might start out like this. It might start here, and now instead of being a flat line, because we have acceleration, it means it's actually going up. Oops, now there's a collision. Okay, maybe now it has a negative velocity, negative x velocity, but that negative x velocity is getting less negative. Oops, and now it collided, now it hops up here, but at all times the acceleration is positive. Maybe now it's almost going horizontally. Oops, now it's going backwards again, but if it keeps going backwards for a while, it again turns to be going forward. Maybe now it's going here. This, oops, it didn't go very far here. Now it's going slightly backwards, almost, not forwards or backwards at all, just up or down. Well, it's turning to do something like this. Maybe it suddenly hits one here and goes up, and so on, right? Because it's kind of the same idea. Every sort of irregular time interval, it's going to completely reset its velocity in a random direction to get a random Vx within a certain maximum minimum. But because of the upward slope, because of the positive acceleration, the area above it is going to be slightly greater than the area below the graph, just on average. So on average, the electron spends a little bit more time going to the right and does so a little bit faster because of the upward slope of the velocity time graph. And that is how you get an overall motion of the electrons to the right. So we get what's called a drift speed. So let's be a bit more mathematical and try to figure out what that drift speed actually is. So the acceleration of the electron is going to be the force over the mass, right? We write out F over m, Newton's second law, and the force is of course the electric field strength times E divided by m. So that implies that the sort of distance gained or lost due to the acceleration in comparison to there being no electric field is going to be given, that's going to give us the drift speed. It's going to be given by the acceleration times the average time, it's called delta T average, the average time between collisions. Can you imagine that if the atoms are super close together, the time is small, they're very big, they're easily hit, they're hard to miss for the electron, it's constantly changing its direction, constantly bouncing back and forth, the acceleration hardly matters at all, but if it's allowed to sort of fly free for a while to the wire, it's building up a bigger speed, so on average it's going to cover more distance going to the right. By the way, this average, this delta T average is often written as tau, which is of course a little bit annoying because we've recently used tau as the time constant in RC circuits, but this is completely different use, right? Again, I guess because it's time, we have to use something that's sort of like a T, and there's only Latin and Greek. We don't trust ourselves to use any other alphabet, and so if we don't use T, we're going to use tau. I guess that's what we're stuck with. So just to be aware, this is not the time constant from, say, RC circuits or some kind of other decaying exponential. It has nothing to do with that. This is another symbol to write the average time between collisions. So what does this depend on? Well, it depends on things like the size of the atoms, size of the atomic nuclei. The bigger they are, the easier they are to hit. Now, whether or not you do that classically, you imagine little balls, or you do it in a kind of quantum mechanical treatment, doesn't matter. You still have a certain, effective area that gets hit or doesn't get hit. Size of the atoms. We have the spacing between the atoms, right? It depends on the material. Right? Those two, this depends on what is it made of. What is the wire made of? Ultimately, how conductive your wire is, right? Materials are different. That's because those things are different between materials. Another thing it depends on, though, is the temperature. the bigger the temperature, the more an atom jiggles. So here's my atomic nucleus. It sort of jiggles this way and this way, right? So back and forth. And if it's a low temperature, it does this. If it's a high temperature, it might do something like this. And it jiggles very fast back and forth. So if an electron tries to come past it, it's more likely to get hit. Even if it's over here, right, it won't get hit by the cold one, but it might well get hit by the warmer one. So higher temperature means you're going to get a lower average time between collisions, because essentially each atomic nucleus presents a bigger target area. In the past, we've talked about light bulbs getting hot and it changing the resistance. Well, that is exactly that effect. Of course, our atomic models here are highly simplified. We're not giving it a full treatment in terms of the quantum mechanics and so on at all. I mean, it would go well beyond this course, but the basic ideas are exactly as we described them here. Okay. So let's now look what that drift speed implies, right? The drift speed here is this thing here. Let me label this. This is the drift speed. Because the electrons are not moving at that speed, they're moving way faster, but overall, if you sort of squint your eyes, it's a bit fuzzy, you can imagine a sort of sea of electron slowly moving to the right as a whole. So how many electrons are actually going to go past some point then? So let's draw another picture here. So here's my wire. Now I'm going to pretend I'm zooming out. I'm no longer sort of looking at the individual atoms. I'm just looking at the sea of electrons here that's slowly drifting sideways, like driftwood in a river. I mean, really it's more like the water itself, but that's kind of how you can visualize it. So I'm going to stand here by the side of the wire. This is me. You can tell again why I'm not getting paid for my art. And I want to count how many electrons are going by this way. This is this person is counting electrons. We're counting them in such a way that if an electron goes past this way, it's +1. If an electron goes past the other way, it's -1. So if this were a wire without the electric field, the person would constantly be counting +1, +2, +1, 0, -1. It would be going up and down because electrons are whizzing back and forth all the time. Because of the electric field, though, you're going to get more electrons going to the right and to the left. And actually, the difference is actually very small, right? Like you get like 1,000,000 electrons going to the left and 1,000,001 going right. Something like that. I mean, it's probably not exactly the right number, but it's like a stupidly large number like that. Right? So it's not 5 go left, 5 go right, 3 go left. It's really like 1,000,001 to 1,000,000. They're drifting very slowly, but on average, they are drifting. So let's forget about the motion of the individual electrons. Let's imagine how could I, in a sense, quantify the number of electrons that are going to go past this point. So this is a little bit like imagining I have a pipe of water and I want to measure how much water goes past a particular point in the pipe. So let's make this sort of 3D surface here, right? It's a 3D pipe or a 3D wire. This is some surface cross-section, right? A cross-section area A for area, because we're imaginative like that. Now, let's say the drift speed is 1 millimeter a second. It's actually fairly fast. And while electrons go many hundreds of meters a second, or way more, the drift speed is usually in the fraction of a millimeter range. 0.1 millimeter a second would be a typical drift speed in a wire in a circuit. So, if we think of these electrons as this kind of driftwood of electrons that goes down to the right, then suppose I ask, how far back do I have to go so that all this volume here of electrons makes it through? And the answer is, of course, if I go 0.1 meters per second, or if electrons drift 0.1 meters per second, then this would be 0.1 meters. So if this is essentially the drift speed, right, times 1 second, then that implies that all the electrons in this volume are going to go through this surface. Electrons, because I only talk about the free electrons, not the ones that are still living with the atoms. And of course, I just mean on average that's what we're getting. Right? I'm pretending now it's all this kind of driftwood situation rather than the back and forth situation, because we're just talking about the average motion of the electrons. Electrons in this volume make it past, what should we call this, the observer within the next second. Almost like we're doing a bit of fluid dynamics here. So what is the volume? Well, if this is a cylinder, but it could be some other shape of cross-section, doesn't matter, the volume of it is going to be the length times the area, right? So volume is going to be, so volume per second, say, is going to be the drift speed times the cross-section of the wire. Okay, so but that's the electrons in that volume. How many electrons is that? Well, we're going to get the number of electrons drifting past per second. And that's what we call the electron current. Give it this little I subscript E. At least that's what the book does. I'm not sure I've seen this particular notation before, but let's go with it. The book uses it, we're going to use it too. Electron current IE is given by, well, the volume times the number of electrons inside the volume. Meaning the number of electrons per unit volume. Excuse me, right? So it's a little bit like the electron density. I think the book uses this notation here for that. This is the electron density. This is how many free electrons are there per volume, per unit volume. Number of free electrons per unit volume. Okay, right, so this is the volume. This volume here that's going to make it past our observer within the next second. And this is the number of electrons per unit volume. So we multiply the two and we get the electrons drifting past per second. Can we rewrite it a little bit? Yes, we can, by rewriting our VD in the form that we had before. I think it's on the previous page. We have it here, right? VD is A times delta T, the average one, and we've got an expression for A. Let's put those pieces together. I'm going to put this onto a new page. We're going to find that the electron current IE is equal to the drift speed, which we're going to write in terms of acceleration and time. It's going to be E over m, the mass of the electron, that's my acceleration, times the average time between collisions. That gives me the drift speed times the cross-section times the electron density there. And this, of course, this quantity, again, depends just on the material, right? I should have added this over here, perhaps, down here, right? This depends on the material. That will also contribute to the conductivity of your metal is how many free electrons are there. The more there are, the more are going to drift past you. And this number we can just look up. For example, the textbook has a table in which, for some common metals, for example, you can read of what that number is. It's a stupidly large number, 10 to the I don't know what, but it's actually only a tiny fraction of the total number of electrons in the actual metal. Okay. So this is my expression for the electron current. So now imagine I don't want to count electrons, I want to count charge flowing past me. Well, charge is the charge passing a point per second is the current. Current I is the what do we mean by that? The charge passing a point per second. Right, that's what we mean by an amp. Right, 1 amp is 1 coulomb per second. And if you have a certain number of electrons per second, well, we just multiply that number by the charge of the electron. Right? Number of electrons per second times charge of the electron. Let me write this down again. So number of electrons per second multiplied by the charge of 1 electron. So if I put that in here, I'm going to get another factor of E, a good factor of E here and E here. The electron charge, so I actually get an E squared. So I'm going to find that I is equal to E electric field strength times E squared over the electron mass times the average time between collisions, which is hard to calculate. Depends on the material, how the atoms are arranged, how dense they are, how big they are, how warm it is, times A, cross-section, times the number of free electrons per volume. It's kind of a chunky expression, but hopefully you see how we got there. It's not something you would just guess, right? This is my expression for the current, but step by step we made our way there. Can we work with that any further? Yes, we can. Let's remember what electric field is. Where's my picture of my wire? With a bunch of sheets here. Let's see if I can find my picture of the wire. There we go. Right. This is my wire from before, and we said for there to be an electric field, we have a high potential and a low potential. So I'm going to rewrite the electric field as the potential difference and the length of the wire. Because remember that the electric field is the potential difference divided by the length. Right? Strictly speaking, we have E, right, is dV dx up to a minus sign, but who cares? So I'm just going to write like this. Never mind. That's, you know the sign, right? It's down the hill. So if I know the length of my wire, right, and I know the potential difference, I can relate those to the electric field. I don't have to worry about the derivative because I'm going to go with the assumption that the electric field inside my wire is constant. And it's a fairly good assumption because what you get to control usually is the potential difference, for example, by using a battery. And then the electric field is going to be constant in the wire. If it was not, it would lead to a rearrangement of charges until the electric field is constant in the wire. So we can go with this sort of finite fraction rather than the infinitesimal one because the electric field is constant. So that means my current, right, I'm going to plug this into here and I'm going to rewrite it a little bit, is delta V times A over L, so I'm going to write it like this, times the rest, which is, if I'm not mistaken, E squared tau times the this thing here, the electron density divided by the mass of the electron. So 3 of those terms, right, and one of them squared, has to do with electrons. Actually, these 2 more have to do with the metal, these ones are just the pure properties of the electron. So does this look familiar? I, the current, is proportional to the potential difference between the 2 ends of the wire that I'm looking at. Then the wire has a length L. Should maybe label this here by L. I mean the length of the wire that I'm looking at. The wire segment across which I'm measuring the potential difference. So we're getting back the idea that current is proportional, right, to the to the potential difference. So that means this whole thing here, right, so CF, conferatur, Latin, right, to be compared with, so it literally means, is, look, delta V divided by R, right? This is what Ohm's law says. In a sense, we derive the fact that for this model of wire, we're getting this. And for a light bulb, we found, hey, it's not quite true. Well, the reason was that actually this thing here changes a little bit as the wire gets hot, right? But it's a different story. So we're getting back Ohm's law in this case. And where now we can identify R, right? R is sort of this whole thing here is 1 over R. So I'm getting that R is going to be equal to L over A, and we're going to keep those out front for a reason I'm going to come to in a second, times ME, the mass of the electron, divided by the charge squared, times tau, times the electron density. Okay, so this would be the resistance in terms of a bunch of stuff that depends on the material that the wire is made of and the properties of electrons. And then those two terms are the geometry of the wire, right? What's the cross section, what's the length. So those two here are the geometry of the wire. And these ones here. And then those ones over there are the properties of the material and of electrons. Other than switching out your gold wire for a silver wire or a copper wire, there's nothing you can really do here, right? But this is the thing where you can say, I take a longer wire, I take a thicker wire, right? You're going to change those quantities. So we're going to rewrite that just in one more way. We're almost there. Already got to Ohm's law, right? But I'm just going to rewrite that as this expression up here. I can show it to you. We can have it up. R, the resistance of a wire, is the geometry of it, times, we're going to combine all those things into one. We're going to call this rho, and we give it the name, that's the resistivity. And I know what you're thinking. You're thinking, isn't rho meant to be the density of charges? Yes, that's just another another case where you have the same symbol being used for more than one thing. I guess here rho is the Greek R, same letter as the resistance and resistivity. It sort of makes sense. Usually the context makes it fairly clear, and in any text that you read, any textbook, somewhere it should define its symbols, right? So there shouldn't ever be a confusion here. Notice that resistivity and resistance are different things. Right? The resistance is of a piece of wire. It could be the filament in a light bulb. But you a specific piece of wire, it has a certain resistance. Whereas this property here is the resistivity of a material. Right? So if I give you a copper wire, and I give you a second copper wire that has a different length and maybe cross section, they will have the same resistivity if they're both made of the same material, but they will have different resistances. So this pretty much takes us to the end of the chapter, at least the part that we haven't talked about already in the context of circuits in chapter 28. Right? So really, the point was we start from a very simple model of electrons bouncing through a wire, and we come back to Ohm's law, and we split up the kind of things that resistance depends on. It depends on the geometry of the wire. The longer the wire, the more resistance. Kind of makes sense, right? The longer the wire, the further the electrons have to go past all those, squish past all those atomic nuclei, the more they have to bounce around until they get there. The area, the cross-section, the bigger the cross-section, the smaller the resistance. Makes sense. It's like you're opening more lanes of highway. If you want to take the highway analogy further, the longer the construction, right, it's the L, the longer the construction, the more it's going to slow down traffic. The more lanes you have, that the electrons can go down in parallel next to each other, the less resistance there is. And then, of course, it depends on the sort of atomic properties and the electron properties that have to do with the material that you usually can't change. We combine that in the resistance. Okay, before we end this video, let me just make a couple more sort of miscellaneous comments, concepts that you might encounter. So other concepts. I'm going to be very fast. One thing is that sometimes you see people talk about the conductivity of a material. And then that's for some reason giving the lowercase sigma as its symbol. I don't know why. That's just 1 over the resistivity. Right? If the resistivity is bigger, it's harder for electrons to go through, harder for current to flow. But lower resistivity means higher conductivity. And similarly, you also sometimes meet the idea of a conductance of a wire. And it's, I don't know what the symbol is for that actually. It's going to be 1 over the resistance. It's silly, right? These are just concepts that sort of, I guess, tell us how easy it is for current to flow as opposed to how hard it is for current to flow for material and for wire. Not really useful, just a different way of rewriting those quantities or describing those properties in a wire. Another concept you might come across is the current density. It's usually given the letter J, capital J, and that is the current as an I per cross-section area A. It's sort of eliminating the A dependence of the current by saying how much, if this is my cross-section of a wire, asking how much of it is going through it per, say, square millimeter. Then as a final little note, let's quickly go back to combining resistors, right? Remember long ago, as in last week, we talked about resistors. And one thing we had, for example, was we put a resistor here and a second resistor here in series, right? R1 and R2. Then the combined R, or the equivalent R, is R1 plus R2. Now, if you look at our expression for the resistance, it has the length of the wire in the numerator. So I could write this as L1 rho over A1 plus L2 rho over A2, but I mean, let's assume the A is the same. It's just one wire, long sort of curly wire here, long curly wire here. It's really just, let me get rid of those, same A, L1 plus L2 rho over A. It's just I add the lengths, right? It makes sense. Having two long pieces of wire and calculating the resistance for each one, the way we did in this video, but if I want to find the total resistance, I just add the lengths. That's consistent with this expression for the resistance. If I've got, on the other hand, two wires that are, or two resistors that are in parallel, right, that makes it easier for current to flow, and you can think of it as you're just adding the cross-section of each wire. So if this is R1 and R2, let's say they have the same length of wire, it just splits into two, you can go this way or this way, then this one would have L is the same both ways, over A1 rho. This is L, R2, let me write down here, so I have space, L over A2 rho. Now what's the combined resistance? Well, it's almost like adding the areas, because if you imagine, like there's 3 highway lanes here, 2 highway lanes here, it makes a total of 5 lanes. Try figuring out what this one is. Right, I'm just adding the areas, that would be the combined resistance. And you'll find that we indeed get back that this is equal to 1 over R1 plus 1 over R2. Of course, 1 over this is this, so I'm going to take this to the minus 1. You can check this yourself, the algebra works out here. So what we found out about cross-section and length is consistent with us essentially treating all resistors like it's a really long, thin piece of wire. Right? And indeed, when you look at a light bulb, say, you zoom in on a light bulb, you just sketch this here, here's my light bulb. Now there's this thin piece of wire that does this. And then there's the big cable out here. Well, this thin piece of wire here is the majority of the resistance, because the area, the cross-section area here is very small. Whereas here it's very big, so the resistance of these wires here that connected to the battery don't really matter. Right? Big A, as here it's the tiny a. So the majority of the resistance in this long wire is here, the majority of the power output is going to be here. So our study of the inside of the wire is consistent with our treatment of circuits, in the sense that we can think of all resistors just as a long piece of wire. So in this chapter, in the homework, you're going to get practice with all those concepts we've covered in this video, but if you understand them, then you've essentially covered the entire chapter. 54 minutes in almost, that's enough of me talking. I will see you in class, have fun studying, work hard, and stay healthy.